Howdy, everyone. Happy Friday and happy March the 12th. And we have a quick chat message. Okay, someone loves this cartoon. Anyway, today is March the 12th. We're just 3 days away from the infamous Ides of March, which comes Monday. I was actually curious how many of you understand this cartoon. So if you get the gist of this cartoon, just send me a chat message and say yes. So we'll see how many people get the gist of this. 1, 2, and not going up very fast. Okay, well, let me remind you that we have an expanding universe, and this is based on looking at the hydrogen atom. And we say that the spectrum of the hydrogen atom has a redshift, which means that the frequencies are shifted towards the lower side of the spectrum. Red is the lowest frequency in the visible spectrum. Violet is the upper end. That's why the extremes beyond that are called ultraviolet and infrared. Anyway, if we have a blue shift, it all of a sudden means that the Doppler effect is in the other direction. The frequencies are going up and the universe is now contracting. So why this guy is saying, uh-oh, if it's going to contract, obviously everything could wind up in the same place at the same time in the universe. I actually like symmetry very much, so I like to think that the current thinking by astronomers, which is that the universe will keep on expanding and expanding and expanding. I'd like to think that gravity catches up with the Big Bang and the expansion slows down, ultimately reverses and everything comes back again, and then we have another Big Bang maybe in 20 or 30 billion years. And so that would be a nice way to picture what the universe is like. If that doesn't happen and the universe keeps expanding, thermodynamics tells us everything is going to go to 0 degrees Kelvin, and for all practical purposes, the universe would be pretty dead at that point. So let's hope someday people are able to observe a blue shift. Okay, we started talking about rotational spectra last time. And as we always do, we try to start simply. And we start with diatomic molecules. So here's a diatomic molecule, which is capable of rotating. We said we had masses m1 and m2. We defined the moment of inertia. We looked to see the definition of the center of gravity. And we came up with a formula that the moment of inertia could be written as the product of the reduced mass times the bond distance that we have. And the reduced mass, which we're going to be using quite a lot when we talk about spectroscopy of diatomic molecules, is just the product of the masses divided by the sum of the masses. And so in this case, then we can say moment of inertia is mu r squared. Okay, so the Schrodinger equation for this can be solved, and I'm just going to show you what it is. We're not going to worry too much about the wave functions for rotations. They aren't particularly interesting, but we are interested in the energy levels of rotation that you can have. So we first write the kinetic energy terms for the two heavy masses, M1 and M2. If this is HCl, then this would be mass of hydrogen, this would be the mass of chlorine. And you'll notice we have an M1 or an M2 in the denominator, and so we could pull these out in front of the kinetic energy term. And up here I've noted 1 over M1 plus 1 over M2 is also 1 over the reduced mass. And I think you can easily find that from this relationship here. So this basically is our Schrodinger equation that we have to solve. It now has the reduced mass in front of the kinetic energy term. And if you go back to your notes, you'll see on page QM46, that's the last part of the quantum mechanics section. It was in chapter 12, it's chapter 8 now. We saw that we could write the energy levels h bar squared over 2I times L plus 1. But here, since we're talking about a different kind of phenomenon, namely rotations of a diatomic molecule, we're going to introduce a new quantum number. So this will be capital J. So this is called the rotational quantum number. And we're going to find that it can have values 0, 1, 2, and so on. You remember when we talked about a particle going around a circle or a particle going around a sphere, we said quantum number 0 giving us 0 energy was okay. It just means the molecule isn't rotating. So if we want to talk about diatomic molecules, we can set J equal to 0, and we just have a molecule sitting there by itself. But we also have lots of other quantum states for J1, 2, 3, many integer numbers. And so the energy levels are going to be 1 times 2 times this quantity, 2 times 3, or 6 times that quantity, and so on. Okay, so we're going to find that these energy levels can be related to this h bar squared over 2I. And so we'll define this as a rotational constant. And then the energy levels are going to be given by this rotational constant B times J plus 1. And this is indeed what we find experimentally when we start looking at molecules. So before we go on, I want to say a little bit about units that we're going to have for the rotational constant. Remember that when we talked about atomic spectra, I liked Ray numbers, which are centimeters to the -1. And if we have an energy level, we can convert it to frequency by dividing by h. So h nu is delta E, as we've seen over and over again in the course. So this is our transformation. We have to divide by h. If we want to go from frequency to centimeters to the -1, the rule is we take frequency, which is in seconds to the -1, divided by the speed of light. And here I'm putting it in centimeters per second, so we can get the result centimeters to the -1. So delta E over hc is what our energy would be if we're using centimeters to the -1. Okay, so why I went through all this is I want to define something called B bar. I've used the bar before for averages and expectation values. Here and in the spectroscopy section, whenever I put a bar on something, that means I want it to be in centimeters to the -1. So we'll put B over hc. And so you'll see this is the formula that I had before. I've turned h bar squared into h squared over 4 pi squared. And we can write this whole business out. I can put the bar back. And then the good news for you is anytime we have to do this calculation, I'm going to give you this formula. Almost always we will want to work in grams and centimeters squared. And so the quantity in the numerator is 28.0 times 10 to the minus 40. So if we can get a rotational constant B bar from a spectrum, we can then directly calculate the moment of inertia from this formula. And notice up here, if we know the moment of inertia, we can immediately calculate the bond distance that we have in a molecule. Mu is readily calculated because we know the masses of the two atoms that we have in a diatomic molecule. So this is what it's all about. Okay, so this tells us what we expect for the energy levels. And now we want to know what are we going to see in the spectrum. And to know that, we have to know what are the selection rules for rotations of diatomic molecules. If we want to look at absorption spectra, either in the infrared region or for larger regions, for larger molecules, we will want to go to microwave regions. The rules are, as I told you last week, first of all, the molecules have to have a permanent dipole moment. And then secondly, delta J has to be +1. So if we start at J0, we can only go to J1. If we start at J1, we can only go to J2. J4 can only go to J5. These are the absorption spectra that we would see. For molecules like HCl or nitric oxide, this will occur in the far infrared region, typically between 20 and 200 or 300 wave numbers. Larger molecules, again, it would go much lower. Okay, so what will our spectra look like? So every energy spacing will be the difference between one state with quantum number J+1 and the other with quantum number E sub J. And this is the formula that you would get if J is equal to J+1. J turns to J+1, J+1 turns to J+2. And then you subtract the original state you start from. If you take this difference, this comes out to be 2b times J+1. And so what I'm about to show you is get a very orderly spectrum where you're going to get bands at 2 times B, 4 times B, 6 times B, 8 times B, and so on. J here represents the lower state that you start from. So when J is 0, you get 2B. When J is 1, you get 4B, and so on. So let me just first show you the spectrum that you get from this. This is not very high quality because it's been Xeroxed over and over again. When I first came to Aggieland more than 50 years ago, I got a nice new spectrometer, and that's one of the reasons I came here. It's made by Hitachi in Japan, and it was the best equipment at the time. And we could take the spectrum of HCl. So you can't see the scale very well. We didn't have PCs or laptops. So you just had a chart recorder and the data came out. So the instrument, even though it was very good, it didn't start quite low enough to see the first band, but I've drawn it in rather poorly here as a dotted band. This would be the J0 to 1 transition at 2 times B, and it would be at about 21 wave numbers. Then this is the 1 to 2 transition, 2 to 3, 3 to 4, 4 to 5, etc. And you can see the nice equal spacing between all of these bands as we go on up. So each of these spacings is 2 times B. And as I told you, once we know what B is, we can calculate the moment of inertia. And from that, we can calculate the bond distance in the molecule. So when we get to the second exam, you can very well expect that I'm going to give you some information about rotational spectra and expect you to calculate a bond distance. But that's how freshman chemistry books know the bond distance in HCl, nitric oxide, many other molecules like that. Okay, well, here's our energy diagram. Again, remember the abscissa has no meaning. We just need room to indicate what energies are possible. This is an energy diagram. Down here, this is energy 0, where you have no rotation. Let's make this a little bigger. And so here are the quantum numbers J, 0, 1, 2, 3, 4, 5. Our first transition is from J0 to 1. That's this band right here. Notice it says it's 2B. For HCl, that comes out to be 21.2 wave numbers. If you do the calculation of the energy levels, J times J plus 1 times B, at J0, you get 2B. At J2, it's 2 times 3, or 6B. Then it's 3 times 4, or 12B. Then it's 4 times 5, and it's 20B. And so on. Next one's 32. So the transitions go 2B, 4B, 6B, 8B, 10B. Every time I look at this, I'm amazed. Mother Nature really created this about as trivial as one could hope. All the nice spacings. This goes directly back to the theory I just presented for you. We use the Schrodinger equation to figure out what the energy levels are, and it all works. So it's quite remarkable when we look at this. You'll remember last time I also told you about the Raman effect. One of our students says he's convinced that we live in a simulation. So I guess that's a Mother Nature simulation, or we're simulating ourselves, or we're all part of a laptop computer. Who knows? Anyway, so you can see it's a very straightforward diagram. You can calculate the energy levels from B times J plus 1, and this is what we observe. Last time, I told you about the Raman effect. This is where we shine a laser onto the sample, and then we look at the frequencies that are shifted to lower values, and then we can have Raman transitions. The Raman selection rule is delta J is equal to 2, and that's a little bit later in your notes. But this diagram shows where they are. So we can go J0 to 2, 1 to 3, 2 to 4, 3 to 5, 4 to 6, and so on. So even though I'm showing a direct arrow, you go way, way up in energy, like 20,000 wave numbers, and then you fall back here to maybe 19,980 wave numbers. But the loss of energy tells you that you wound up on the first rotational state. So Raman, then you can see the bands would be at 6B, going from 0 to 6B, then 10B, going from 2B to 12B, then 14, 18, and so on. So it's a little bit different, but from Raman spectra, you can also get rotation values. Now remember that diatomic molecules like O2, N2 that are homonuclear, they don't have a permanent dipole moment, so you cannot study absorption spectra of these molecules. But Raman spectra can be looked at all diatomic molecules. So if we want to know the bond distance in O2 or N2 or F2 or even Hg2, that exists, that's the mercury dimer molecule, you get that from Raman spectroscopy, and we know that that data then winds up in freshman chemistry books. Okay, so this is what I've been concluding, and the value of what you can do for this case, diatomic molecules. We know B bar from the spectrum. We know the constant here, 28.0 times 10 to the minus 40th. From that, we can calculate the moment of inertia. From the moment of inertia, we can calculate the bond distance r, since we can easily calculate the reduced mass. So all of this is pretty straightforward. There are some practice problems within your lecture notes. And as I said, you can count on having a problem of this type when we get to the second examination. If you go back to this spectrum, it's not quite totally obvious, but hopefully it is. You can see that the intensity of these bands increases for a while, and then they start to decrease. And so the question is, why should that be the case? In almost every quantum mechanical situation, the lowest energy state is the most populated unless we have a degeneracy. And indeed, for molecular rotations, we do have degeneracies. So last week I told you that band intensities are proportional to the transition moment integral, but they're also proportional to the population of a state. And so it turns out that the population of any of these rotational levels, each of one which is identified by a quantum number j, it has a degeneracy factor, 2j plus 1, and then we're comparing n sub j to the ground state, n0, and then it's e to the minus e sub j over kt. This last term we talked about last time, it says if energy levels are close together, they can be more highly populated, or if the temperature goes up, higher states are more populated. The degeneracy here, 2j plus 1, is similar to what we discussed when we talked about the L quantum number for atoms. Remember for atoms, when L is equal to 1, you have a p orbital, and the degeneracy is 2L plus 1 or 3, there are 3 p orbitals. When L is equal to 2, 2L plus 1 is 5, those are d orbitals, and there are 5 d orbitals. And that comes from angular momentum components. So when these diatomic molecules rotate, they're also going to have different components. And the degeneracy will be 2j plus 1, just like the 2L plus 1 we had for atomic spectrum. So this is something you need to be aware of if you want to calculate what is going to be the most populated energy value that you have for a system. So please understand when we say a level is degenerate, let's say we're at j equal to 2, the degeneracy is 5, that means there are actually 5 quantum states at that same exact energy. They will have distinct wave functions, but the fact that there are 5 states at that energy gives us 5 times more chance to have molecules at that energy. Okay, so how do we explain the apparent increase in intensities in that HCl spectrum? Here's a graph of 2j plus 1. It's just a straight line, as we can all tell. And then here's the exponential curve, which goes down at higher j values because we're going to higher energies. In reality, these curves are not continuous because we only have values for J0, 1, 2, 3, 4, 5, etc. But nonetheless, I can present it this way. And then I can take the product of 2j plus 1 times exponential, and you see it goes up like this, and then it finally drops. So going back to HCl, we start low. Here we had a degeneracy of 1. The degeneracy is 3, 5, 7, 9, 11, 13, 15. So it goes up for a while, but after a while, the relationship or the ratio of degeneracy being 11, which it's here, or 13, the increase is smaller than the decrease due to the exponential term. So these finally die out. Notice this transition is from J11. So the energy of this state is 11 times 12, or 132. HCl B value is about 10. So we're looking at it being about 1,400 wave numbers above the ground state where this transition starts. And as we'll learn in the latter part of the course, each of these 23 degeneracy states will only have about 1% as much intensity as we have in the ground state. So we do expect this to die out at room temperatures. If you made HCl really cold, we might only see a few of these transitions. If we heated it up to 300 degrees, say, we'd probably see transitions up to J20 or something like that. Okay, so that explains the intensity pattern. I already told you about the Raman spectra. So first transition would be 0 to 2. We go from E0 to E2, 6B. 1 to 3 gives us transition from 2B to 12B or 10B. 2 to 4 is 6B to 20B, and so that's 14B. So after a first big jump, so the laser beam would be right here, the laser frequency. The first level would be 6 times B lower, then the next 10B lower, then the next 14B lower, and so on. So first spacing is 6, and then 4B after that. I can ask a more subtle question on the second exam. I can give you separation between two Raman rotational bands and ask you for the bond distance from that, for example. And as I said, there are a bunch of practice problems in your text. Okay, so here's a picture of our energy diagram and the spectrum that you actually see. So you notice the Raman transition showed going 0 to 2, 1 to 3, 2 to 4, 3 to 5, 4 to 6, and so on. As I've said before, the transition isn't directly 0 to 2. You go way up here to something like 20,000 wave numbers, and then you fall back on level 2. And so that's what this band would be here. This would be 6B lower in energy. I think this might be a spectrum of carbon monoxide. I don't remember for sure. But you'd have 6B, 10B, 14B, and so on. Last time, I also told you that we would not normally talk about anti-Stokes Raman lines, but these are transitions that start from upper states and go to lower states. So this first transition here would start at J2 and come back to 0. The separation would still be 6B, but it would be 6B higher than the laser line. If this gets confusing for you, that's just ignore that. When we talk about Raman bands, we're always going to focus in on Stokes lines. One of the main reasons for that is excited states very quickly diminish in populations. And so when we look at vibrations, for example, you're not going to have many molecules excited up to 1,000 wave numbers, for example. So in rotational spectra, the anti-Stokes bands can be quite strong, but when we get to vibrational spectroscopy, it's not very strong at all. Incidentally, I told you that the Raman effect was discovered in 1928 when there was the 50th anniversary for the Raman effect. I was one of 10 Americans invited to partake in the celebration of that. And it's kind of hard for me to believe that's now 43 years ago. So we're approaching the 100th anniversary of the Raman effect. I don't know if some of you have heritage from India or some of you have been there. When I was there, it had about 600 million people. Now it's about double that. So population explosion is pretty great. India was extremely poor when I was there. I can't help but think it must even be poorer. There has been some technological advances. A lot of times if you have problems with your Dell computer or your TI calculator and you call for help, you wind up talking to somebody in Bangalore, which is in fact where we had our Raman conference in 1978. But anyway, what I wanted to tell you was the way that Raman discovered the Raman effect. There were people like a German scientist named Smeckel and an American scientist named Wood who had predicted a lot of these kinds of effects. And Raman read the papers and he took a test tube of benzene. He took sunlight, shone it through a prism, and he chose just one color of light, probably something like blue. And he would shine it onto the benzene in the test tube, and he saw a lower frequency color come up. And he said, aha, I have proven and seen the Smeckel effect. But Raman got the credit for it, and so this is called the Raman effect. The Russians also had people work on the theory. I think the fellow's name was Malmstadt. And so I don't know if even today the Russians call this the Ramen Effect. They probably still name it after the Russians who had developed the theory. The Germans for a long time called it the Smeckel/Ramen Effect, but nowadays universally most people call it the Ramen Effect. Unfortunately, I write a lot of papers on the Ramen Effect, and anytime I type in the word ramen, it changes it to Roman, and so I have to fix the spell check that I still want ramen in there rather than a Roman effect. Okay, so all of that's pretty straightforward, and that's pretty much what we want to say about the spectra of diatomic molecules. But now I have to tell you that, again, I've lied to you a little bit. You remember I told you that I lied to you a little bit about bandwidths, that delta E isn't always exactly h nu. There's sort of a little plus or minus thanks to Heisenberg and Doppler broadening and so on. Well, the correction we have to make for rotations comes from centrifugal distortion. So up to now, we've been saying the energy levels are B times J plus 1. This is based on the rigid rotor. And the rigid rotor model, as I've told you, is based on the fact that we have a fixed bond distance for a rotating molecule. I think we're all familiar with the centrifugal effect, though. The classic case is you take a bucket of water and you swing it around your head and stuff, and you don't get wet because the water tries to go away from you. Or a mini experiment you can do is you can take a couple of whatever you want, piece of couple of dice, for example, hook them to a rubber band, swing it around, and you find the rubber band stretches. So what happens in a diatomic molecule when it swings around like this, the bond actually wants to stretch. And so when you get to higher J values, you're going to have a longer bond than you have at lower values. So that means this formula is not going to work exactly. And when you go through the quantum mechanics of it, you have to add the centrifugal distortion term. But if you remember our HCl spectrum, you saw this first part worked pretty well. We didn't really have to worry about much corrections. So let me show you the magnitudes that you actually have. For HCl, the rotational constant is 10.34, and this distortion constant is 0.0004. So if J is just 2 or something, then it'd be 4 times 3 or 12 times this number, and it's still very, very much smaller than B. But when you get to higher levels, like J equal to 10, then the second term becomes 10 squared times 11 squared, which is roughly 10 to the fourth. So when you take 10,000 times this number, you have a real correction that you have to deal with. So here's an example of what happens. The observed value for a 10 to 11 transition in HCl, which actually I showed you in that spectrum, is 226.5. Sorry, I have to let that phone ring out. It's a physics professor calling me, and I don't want to be rude and just click him off again, but it'll finally stop. Okay, so the observed is 22.650. If you don't do the correction, you can see you're one wave number off. So it's about 0.5%. So it's not a very big effect, but it does show that it's coming into play at higher transitions. If you do put in the D correction, you can see that you're going to be correct to about 5 parts in 10,000, I guess that is. Okay, so that's pretty much the story for diatomic molecules. And the good news for you is that we're not going to spend much time on polyatomic molecules, and we don't need to because the concepts are pretty much the same. The only difference is that instead of having just one rotational constant for a large molecule, you're typically going to have three. So this amoeba-like thing is supposed to be a large molecule in the vapor phase. We can put in X, Y, and Z axes. The definitions of the moment of inertia, IXX, IYY, IZZ, about the axes, are defined as mass times the distance squared from each of those axes. So we're going to wind up with three moments of inertia, and each will give us a rotational constant. So I'll go through very quickly different types of larger molecules we can have. If I had more time, I would show you where this comes from. If you have molecules where all of the moments of inertia are the same, like for octahedral SF6 or methane, then you can directly write one simple formula for that. And all three of those rotational constants are going to be identical, and you're going to have exactly the same formulas for the energy levels. Sadly, for spherical top molecules like methane and sulfur hexafluoride, you cannot see any of the rotational spectra in either infrared spectra or Raman spectroscopy. Now that might make you think we're not going to be able to get rotational constants and we can't get bond distances. There are more advanced techniques in spectroscopy where we look at combinations between rotations and vibrations that will give us the data. So for example, when we take the vibrational spectra of methane, there will be rotational fine structure, and we can get what the B values are from that, and we can learn about that more. Okay, so spherical tops are really symmetric. Molecules like benzene are a little bit less symmetric, but also quite symmetric. And so here's an example that two moments of inertia in the plane of benzene are going to be the same. And then there's going to be a unique moment of inertia perpendicular to that. You're not going to be responsible for doing any calculations like this. It's just slightly more advanced than having to do your diatomic molecules. But for benzene type symmetric top molecule, you still have your rotational constant B, but you have to add a second constant that's called A. And then your energy levels come out in terms of two quantum numbers, J, just like we've had all along. But then there's a second quantum number K, and this is related to the rotation about a unique axis that you have in the molecule. And so you'll notice benzene, for example, has a unique axis, the one we've labeled I parallel, the one that's along this most symmetric axis for rotation. That would be the one that K relates to. Now, most molecules, of course, are asymmetric top molecules. And so okay, the question is, why don't Raman techniques work for spherical molecules if they work for homonuclear diatomic molecules? If you remember the selection rule I gave you for Raman spectroscopy is that you had to envision the change in shape as the process takes place. If you have a spherical top molecule, then as far as radiation is concerned, every direction is the same, and radiation is trying to interact with a spherical ball. So it gets much deeper than that into the mathematics, but it's simply the requirements that are required for Raman just don't work when you work out the quantum mechanics for it. But very valid question to ask. All right, asymmetric top molecules, most molecules are of this type. You get three different rotational constants. A is different from B, is different from C. And so it might seem like if you get a larger molecule, how can you possibly figure out enough structural parameters to figure out what the molecule looks like. Well, a lot of this work is done by microwave spectroscopists, and they're very good at looking at isotopic species. Organic molecules, every carbon atom, its natural abundance of carbon-13 is 1%. There are natural abundances of oxygen-18. You can also dope the molecules to give you higher natural abundances with D. Deuterium, this is isotopic mass 2. I don't know what the price is, but you used to be able to go to the chemistry stockroom for something like $20. You could get 100 milliliters of D2O. That's the deuterated form of water. So it's very easy to put deuteriums on in place of hydrogens in many molecules. But let me show you how structure determinations work. If you take the spectrum of water, let me see if, okay, here's the rotational spectrum of water. And so you can see it gets to be very complicated. And I want to show you why it gets to be very complicated. Here are what the energy levels wind up being for an asymmetric top molecule. So we have rotational constants A, B, and C, and this is a labeling scheme for what the different levels are. But you can see that every level can actually be calculated. But the spectra get very complicated, and so when you go to water, I or anyone that isn't a superb rotational spectroscopist would have a very high chance of not being able to explain it. Someone asks if you drink it like regular water or do you die? I refuse to answer that question because you might try the experiment on somebody. Now, I'm partly joking, but to be honest, I'm not sure of the answer, but it's probably not good for you because there are kinetic effects which actually come from 0-point energies of molecular vibrations. You remember we talked about 0-point energies for translations, and then we talked about 0-point energies for the harmonic oscillator. H2O and D2O have different 0-point energies, so the dissociation energies of those two molecules wind up being different, and so chemically they are not identical. But I don't know how sick it would make you. There is a natural abundance of deuterium in your regular water. I think it's like 0.04% or something like that. But anyway, so don't drink it. Okay, but here's the summary then that you can figure these things out. All right, so what I wanted to tell you is there's no problem if you're a good microwave spectroscopist. You get 3 rotational constants for water. You can write your simultaneous equations, and you only have to decide on 2 parameters to figure out what the structure of water is. There's a bond distance, and there is a bond angle. So you only need 2 structural parameters, and you know the structure of water. But this is how we know the bond distance and bond angle of water. It's from the rotational spectrum that I just showed you. Now, what happens if you go to hydrogen peroxide? So hydrogen peroxide has 2 OH bonds, so 1 parameter needed there. It has 2 equivalent angles, HOO, and it has a OO distance, so that's 3 structural parameters. But then you also need to know a dihedral angle. It turns out that tau here for water, it does not make hydrogen peroxide either trans or cis. It's gauche, it's somewhere in between. So I think this angle might be 108 degrees, or I'm not quite sure exactly what it is. But the point is you need 4 parameters to be able to figure out what the structure of this molecule is. Well, most of you at some time probably used hydrogen peroxide. When you buy it from the pharmacy, it's about a 5% solution. So you know it's mostly water. Okay, I'll Uh, Another physics professor, sorry about that. Anyway, the point is you can very easily make deuterated hydrogen peroxide. You can just put in small amounts of H2O2, throw it in the water, and the deuteriums and hydrogens are exchanged. And then you take out the hydrogen peroxide, which now has become the deuterated form. And so when you have both the deuterated form and the hydrogen form, you have a total of 6 rotational constants. You need to only determine 4 unknowns, and so you can easily do it. When you get to larger and larger systems, just from experience, you know that in aliphatic compounds, carbon-hydrogen bonding distances are 1.087 angstroms. And you can transfer a lot of data from molecules to molecules, but you can still get a lot of data from there. Somebody asked, is any of this stuff going to be on the exam? There won't be any quantitative questions, but there can be concept questions. And so I want you to have a basic idea of what's going on when we're looking at these kinds of molecules. Okay, so we saw the formulas, we saw the spectrum of water, and then this table is actually out of one of the books I edited. We know a lot about molecules in space from, it's normally called radio frequency spectroscopy, but it's really looking at microwave regions. And there are several things I want to emphasize. If on Earth we see that here's a band for formaldehyde, we don't immediately conclude we have formaldehyde flying around in space. It's only when we see lots of bands for formaldehyde, here's another one, here's another one, and we confirm in many different places that we know what these molecules are. So this is just an example of the kind of things you can look at. And this is in a very narrow region of the microwave spectrum. So this is gigahertz. All of us now know about gigabytes, so now you know what gigahertz is. That's how many cycles per second that you have for the spectra. But it gets to be pretty interesting to see what some of the molecules are in space. A lot of them have also been identified by vibrational spectroscopy, but we get a big idea of what's out there when we look at these systems. Here's kind of, I think this is also from that chapter in the book. This is from the 2009 book, and so this can easily be very much updated. Here are diatomic molecules observed in space. Let me make it a little bit bigger. Triatomic, 4 atom molecules, 5 all the way up to 12. Bigger and bigger molecules get harder and harder to observe. I want to show you something interesting here. Whoops, it's not this one. I want to look at the 3 atom molecule. Okay, do you see CCH here? This is acetylene with a hydrogen stripped off. So to be absolutely sure that this had been seen in space, somebody on Earth had to knock a hydrogen atom off the acetylene molecule, record its spectra and see where its bands are, and then the radio astronomers went out to look for it, and indeed they found it. Now, why should this molecule exist in space? Well, the molecules are very far apart. So this is a stable molecule. It can fly around for a long time. Maybe in 5 years, it finds another molecule to collide with and becomes something else. We don't see acetylene itself because it doesn't have a dipole moment. So that's the sad part. When we have things like H2, N2, O2, we don't see them directly in space. It says it's got H2 here, but this is probably from an excited state that we can observe. Very common molecule in space is this one. You can hardly read it. It's H3 plus. And you remember when we talked about the Huckel method applied to the H3 molecule, we saw that H3 plus would be a lot more stable than H3 by itself. Okay, so here I'm just trying to give you an appreciation for what you can learn from rotational spectroscopy beyond just getting molecular structures and so on. One molecule, by the way, let me see if it's on the list here. There's a molecule called cyanogen, which is CN. I don't know what order this is, but anyway, it's carbon bonded to nitrogen. And that molecule serves as a very good measure for what the temperature of the universe is. So I showed you what the population formula was for some of these molecular transitions. And using that, if we look back at spectra from CN molecules from like 1 billion years ago, we can calculate out what the temperature of the Earth was there. Why is CH not an ion? Because it doesn't have a charge on it. That was a question. So don't think of these as normal molecules. CH minus and CH plus have probably also been studied in space. Many of these are not the most stable forms, but molecules can fly around in space because they are so far from each other. When you're trying to do something in the laboratory and you have some SO, for example, I don't think that's a normally stable molecule. That would quickly become SO2. But out in space, it doesn't find another oxygen molecule to interact with, so it just stays SO. Okay, so that finishes up on rotational spectra, and we will continue with vibrational spectra on Wednesday. Any quick questions before we continue?